Hello, Calculus 1. Welcome. We started chapter 2. That's where calculus starts. There's a chapter 1 of our book that's a review of pre-calculus. But chapter 2 begins calculus, and section 1, section 2.1, isn't really a lot of work to do. There's a few problems. It's definitely a good read because it asks you, what is calculus? Or it tries to answer the question, what is calculus? Which is kind of a difficult question I've taught calculus for years. We got 15 chapters of calculus in our book. So what is it? And our book tries to say this. Our book says that in pre-calculus mathematics, you can find the slope of a line, of course. I'll just remind you, you find the slope of a line by doing the change in y. You have 2 points. You subtract the two y values. You subtract the two x values. You get the change in y over the change in x. If you're stepping into this calculus class, I'm sure you know how to get the slope of a line. Or I hope you know some pre-calculus, easy algebra. Anyway, in calculus, we can find the slope of a curve. And what that amounts to, and it's chapter 3 before we really get into this, but we start doing it a little bit in chapter 2. It amounts to finding the slope of that tangent line to the curve. So that's a new idea. And what takes us from pre-calculus to calculus, what crosses the bridge is this idea of limits. So we do limits. And so taking a pre-calculus idea, introducing the idea of limits brings us to a calculus concept, the slope of a curve. I might explain that a little bit better. Here's another one. In pre-calculus, everybody knows you can get the area of a rectangle. You can even do that before pre-calculus, third grade. You can find the area of a rectangle. In calculus, though, employing the limit process, you can get the area under a curve. So that's the deal. I mean, they say pre-calculus stuff is a little static, and you can use the limit process to explore calculus, which is the mathematics of these curvy objects. And the world is curvy and changing. Some I've heard calculus is the mathematics of change. This slope is a rate of change. This slope at a particular point is an instantaneous rate of change instead of some average rate of change. So Richard Feynman, the famous physicist, famous teacher, you could look him up, he said calculus is the language that God talks. Calculus is the language that God talks. So we better learn it. You know, you can Google what is calculus, and you could, of course, read about that. Like I said, our chapter 2.1 in the book tries to explain these concepts. You know, what we start to do is we start to use infinity to explain these concepts and to talk about limits. You know, real quick, and this isn't, but to do this slope of a curve, you know, what we do is we have these 2 points, and if I drew that line, you know, that's not the slope of the curve. That's some average slope between those 2 points. But if and so that's just the change in y over change in x, like we said, that's the slope. But if I do the limit, watch this. This is the notation, and I'll teach you limits in the next video. But if I do the limit, LIM, as delta x, that delta x approaches 0. What that means is this change in x between these points gets smaller and smaller and smaller. And we know we can get infinitely close. We can approach 0 without really getting there, right? In numbers, in theory, we can approach things infinitely. So using the power of infinity is kind of what takes us, in limits, takes us from pre-calculus to calculus. So you can see it happening. You know, a good animation might be nice, but there's good pictures. As delta x goes to 0, this x is getting closer to this x. That change in x is getting small. That change in x is going to 0. That line is approaching that line. When I get really close, The slope of that line between those 2 points practically is the slope at that one point. So it turns into the slope at one point. It turns into the slope of the curve. The slope of the curve, we call it, or the slope of the tangent line to the curve. Again, we'll get there. So this is a big idea in chapter 3, the slope of a curve. This is a big idea in chapter 5, the area under a curve. And to get there, we have to learn about limits. So chapter 2 is about limits. You know, and again, using limits has to do with this infinity idea. You know, here's one idea of infinity. You know, what is 1/3? Well, you take 3 and divide it. Can you make 1/3 a decimal, please? Well, you probably know the answer, but you take 3 and you divide it into 1, and you put a decimal point there, and you add as many zeros as you want. 3 goes into 10 3 times. 3 times 3 is 9. You subtract, you get a 1. You bring down the 0. 3 goes into 10 3 times. You bring a 9. You subtract, you get a 1. You bring down the 0. 3. And so how long do you want to do that? An infinite amount of time. Those little dots mean that'll be infinity. I mean, if I just stopped and called this 0.3, that's not right. A 0.3 is 3/10. 3/10 is not 1/3. So I could have called it approximately 0.3. But it's better if it was 0.33, but it's even better if it's 0.333 forever. So, I don't know. I'm using infinity. You know, here's another one. I'm going to draw a line. Here I am. I'm going to start here. I'm going to go halfway to the edge of the board. So go halfway to the edge of the board. Okay, good job. Let's go halfway to the edge of the board. Okay, good job. Let's go halfway to the, all right. Let's go halfway. Okay, let's go halfway. Let's go halfway. Let's go halfway. Theoretically, I could do that forever. This ink is a little fat. The wall is, the molecules of the ink ran into the wall there. I'm sorry. But theoretically, I could do that forever, infinitely. There's always a little space between here and halfway to the wall. There's always a little bit more space, and you could go half of that space. And that's what we do on a number line. This 1/3 sits on a number line. That 0.3 is right there. 0.333 is right there. 0.3333333 is right there. We're getting closer and closer to 1/3. We're using infinity. We're using infinity. So that's kind of what limits do. They use the power of infinity, the idea of getting closer and closer to something. Here's one more thing I wanted to do. So calculus was invented by Newton and Leibniz in the 1600s, late 1600s. Newton was in England, Leibniz was in Germany. They were competing maybe a little bit. They were also writing some letters back and forth, emails. No, they didn't have email. But Archimedes, man, in about 250 BC, Archimedes came up with this idea to find the area of a circle. Watch this. I like this idea. So you have a circle, and you want to find the area. You divide it into 4. It's like slicing the pizza into 4 pieces. And this is the radius. All the way around the pizza is called the circumference. That's the circumference, C. The distance around. The radius is R. And if I took these pieces of pizza here, and there's 4 pieces. Is that what I said? There they are. Those 4 pieces of pizza. This distance would be R. And this distance would be half the circumference, right? That would be 2 pieces of pizza. So that would be half the circumference, C over 2. Half the circumference from here to here. Okay. All right, let's do it with 8 pieces of pizza. Let's do it with 8 pieces of pizza. All right, sorry, need a little space here. And you got to bear with me while I write this out here. 8 pieces of pizza. We get this picture. sorry. Again, the radius is r, and the circumference over here, or this distance, is c over 2. It's a curvy little distance, and this is a curvy little distance, but maybe you're starting to think it looks like a rectangle. Are you thinking that yet? I tell you, it looks more like a rectangle if you take half this piece, cut this piece in half, and bring it over here. Bring half a piece of pizza over there. Now it looks like it's got a distance r, and it's still got this curvy side c over 2. Well, Archimedes figured even in 250 BC he could do this infinitely. And if you do it infinitely, you get a rectangle. I mean, it's not a rectangle, but this approaches c over 2, this approaches r, and the area of a circle can be modeled with this rectangle with infinitely thin slices of pizza, and it's c over 2 times r. Now, we don't think of area, we got a different formula for area of a rectangle. It took them a while they had to calculate pi. That took some other work. That took some infinite work. What do we call a rectangle? A circle? Pi r squared. The area of a circle is pi r squared, is what we usually say. Let's see. It turns out the circumference is 2 pi r. So hang on. If that circumference is 2 pi r over 2 times another r, there you go. The 2's cancel. There's your pi r squared. So this is it. This is the area. This area of this rectangle is the area of this circle. So just an example of using infinity and slicing things up. We do a lot of that in calculus. So that's my answer. I'm going to teach you more about limits now. Thank you.